Hi, I'm Dustin Goetz, and I conducted this project at the University of Southern California. Today I will be presenting a novel wearable haptic device that we have designed. So, one common problem with wearable haptic devices is that they often contain rigid components, which are cumbersome and uncomfortable for users. The problem is amplified for multi-modal devices that need multiple actuators. Our solution is to create a multi-modal device that only uses one actuation method. Our device uses flowing water at various temperatures to transfer heat to and from the user's skin, while simultaneously providing pressure cues. The design for our haptic sleeve can be seen in the top image. The sleeve has four actuators. These actuators are pouches with channels that water can flow through. The pouches and the pouch design can be seen in the bottom two images. A control system is used to regulate the temperature of the water and its flow into and out of the pouches in the haptic sleeve. The system has two tanks that store 15 degrees C cold water and 45 degrees C hot water. First, water from these tanks are mixed proportionally using circulation pumps to obtain a desired temperature. Then the water flows into the actuators, inflating the pouches. Next, the water is quickly evacuated from the actuators using a vacuum chamber. Finally, it is recycled to the two tanks using a peristaltic pump. Valves are used to control the state of the actuators. Each actuator can be at one of three states: maintaining constant volume, increasing in volume, or decreasing in volume. An input matrix is used to specify the state of each actuator at discrete instances of time. Using this system, different haptic patterns can be displayed to the user. We took quantitative measurements on the device to determine its capabilities. It was able to display temperatures ranging from 17 degrees C to 42 degrees C. The graph on the right shows the system's ability to display a specified temperature. The system was able to inflate an actuator in 2.3 seconds and deflate an actuator in 2.2 seconds. This actuation rate is similar to other pneumatic haptic devices. A user study was conducted with 14 participants. Our patch device was compared to a rigid uni-modal haptic device that uses voice coil actuation. In the study, two haptic patterns were used: a pulsing pattern and a stroking pattern. During the pulsing pattern, each actuator is inflated and deflated individually in a random order. After feeling the pulsing patterns, participants were asked to identify the order of actuation. The accuracy of the responses for each device can be seen in the left figure. During the stroking pattern, each actuator is inflated and deflated in succession, starting at the wrist. The users were then asked to rate their emotional responses to the stroking patterns. The interquartile ranges of the responses are shown in the right figure. The users were asked to rate other performance metrics such as mobility of the sleeve, comfort of the sleeve, strength of the pulsing pattern, and continuity of the stroking pattern. The patch sleeve was found to be statistically significantly more mobile than the voice coil sleeve. There were no other statistically significant results. Overall, our multimodal device had similar results to a rigid uni-modal device and showed higher mobility. This result is significant as this actuation method and design could be used to inform the development of the next generation of wearable haptic devices.